What's up, y'all? It's Fuego. This is the second video in an 8-part series about Python libraries for data science and machine learning. If you haven't seen my first video on NumPy, be sure to check that out. But today we're going to be talking about SciPy, a library with a lot of similarities to NumPy, but with much more scientific processing power. While NumPy defined our base object, the NumPy ND array, SciPy creates a lot of common mathematical and scientific subroutines that work on top of this array that make building complex scientific systems much easier. So in this video, we're first going to talk about the similarities and differences between NumPy and SciPy. Then we're going to talk about the libraries within SciPy and kind of categorize them into beginner, intermediate, and advanced categories. And finally, we're going to give some basic examples of SciPy usage and one kind of more complex example that shows the differences in the APIs between the two. If you want the code for this video, it'll be at this GitHub link, which is also in the description box. Let's get into it. So the first thing that confused me about NumPy and SciPy was the difference between numerical and scientific computing. I honestly think that it's really a difference of semantics. While NumPy provides numerical computing on ND arrays, SciPy really focuses on scientific computing. However, there's a lot of overlap between the two libraries. The first thing that you'll notice is that NumPy and SciPy have two libraries with the same name, FFT and linalg. Their functions are very similar, and their APIs are also pretty similar. If I had to guess, these functions were written in NumPy as a quick and dirty way to do some scientific processing, but when they realized that it would be better to refactor it into a separate library, they didn't remove the modules that were already in NumPy to allow for backwards compatibility. And the main difference besides the modules that NumPy doesn't have that SciPy includes is the fact that SciPy is typically faster. It also supports BLAS and the POC specification, which is kind of a standardized specification for linear algebra systems, so if you need that, then you should probably use SciPy. So one thing to note is that SciPy's algorithms run much faster when you increase the size of an array. So we see in this example, we're evaluating the Fourier transform on a single dimensional array of increasing size. One could imagine that after running for millions of iterations, we could add days, if not weeks, to long-lasting processing algorithms. However, we only see small speed improvements on operations on single arrays like this. You're running out of time now. So now that we understand the main similarities and differences between NumPy and SciPy, let's get into an overview of the modules that exist within SciPy. Now, I said this before, but SciPy contains tons of useful scientific processing modules. I think that these can be categorized as either beginning, intermediate, or advanced, depending on their application and the complexity of their use. So in the beginner section, I would include the linear algebra and FFT modules because those are the ones that overlap with NumPy, and they're pretty simple in their APIs. Additionally, I'd include the SciPy stats functions, which include statistical functions like continuous, multivariate, and discrete distributions. It does a lot of summary and frequency statistics. It also does correlation functions, statistical tests, and much more. Now, I'd include these in the beginner section because a lot of their APIs are very simple, in which they take in an array and they output another array. So when we get in the intermediate section, we get into submodules that you really have to look at the API for their usage. This includes a SciPy ND image submodule that contains functionality for multi-dimensional image processing, including filtering, interpolation, morphology, things like that. There's also an IO submodule that allows you to load and save files in a whole bunch of different formats for different external systems like MATLAB. It's great for cross-domain functionality. Additionally, we have SciPy Signal, which is a lot of signal processing functions, convolution, correlation. You can create splines, do filter design, wavelets and waveforms, audio and spectral analysis. There's a lot of things you can do with that. It's a really powerful signal processing library. Additionally, we have the SciPy Interpolate submodule, which contains functionality for the interpolation of single or multi-dimensional arrays, as well as creating splines and a few advanced functions such as Lagrange polynomials and other different polynomial estimation tools. Now let's get into the advanced libraries, and these include the SciPy Integrate libraries, which contain functions for integrating over single and multiple variables. It also has ordinary differential equation solvers, so things for calculus. We have the SciPy Optimization library, which allows us to optimize objective functions like least squares. We can do curve fitting, root finding. We have the SciPy Spatial library, which contains functions for spatial algorithms, as well as data structures for these algorithms. Think geometric computing, convex hulls, Delaunay triangulation. Additionally, we have the SciPy Sparse library, which includes functions for sparse matrix processing, including compressed sparse graph routines, sparse eigenvalue problems. We also have the SciPy Special library, which contains special functions. I really think most of these functions are mathematical physics functions, and also some functions that were not really meant to be used outside the SciPy library. You're running out of luck now. Now we did go over the FFT submodule briefly, which is cross-listed with NumPy, but I wanted to get into a few other examples of SciPy usage. We can first look at that linear algebra module, which is really useful for validating matrix properties and algorithms, or even just homework, honestly. It contains matrix property functions such as the determinant, the norm, and the inverse. One thing to note is that we can use the inverse to do the least squares problem, but we can also solve this type of problem directly with NumPy. This could be really great for solving least squares polynomial systems on really large data sets. Now there are other things we can do, such as matrix decomposition. We can do eigenvalue decomposition and singular value decomposition, but it's really important to look into these APIs because the outputs given by the functions might not be always what you think on a scientific level. For example, the linear algebra eig function, if you don't put any other arguments in when you pass in the matrix, you'll actually get the eigenvalues on only one of the eigenvectors. So you should really look at the API before you use these kinds of functions. Now I wanted to get into a little bit more complicated of an example. You can create a cumulative distribution, which basically tells you at each point in the data set how much of the data set has a lower value than that specific number. So if we create and sort an array and create a cumulative distribution, making sure that it's monotonically increasing, then this function becomes linear. And if we interpolate the array, the CDF of the interpolated array should be the same as an interpolated version of the original CDF. This might get a little bit confusing, but it's just so we can make sure that we're using the interpolation function correctly. This example will be going over the SciPy interpolate submodule. After we import the interp1d function from the SciPy interpolate submodule, we have to understand how it works. The way that this actually works is we pass in an array to that function, which outputs another function that will evaluate the interpolation at each of the points that are input to it. The way we're going to do this is we're going to first create a function for both interpolating the original array and the CDF of the array. Then we're going to evaluate those interpolation functions at every other point within the original array and CDF. Then we're going to see, does the CDF of the new interpolated function match the interpolated CDF? And we see that it does. So this example just shows us how we use this interpolation function and what kind of behavior we can expect. So by default, this interp1d function does linear interpolation, but we can do other things like bilinear, cubic interpolation, but because the CDF is linear, we want the interpolation function to behave linearly to evaluate the quality of the interpolation. Depending on what your application is, the SciPy submodule that you need may be different. Definitely look into any of the tutorials that relate to your specific work. And if you want the code for this video, it'll be at this GitHub link, which is also in the description box. That's it for this video. In the next video in the series, we'll be talking about Plotly and Matplotlib, which are two really powerful data visualization and graphing tools that provide very distinct solutions. So if you're interested in that video or any of the other data science and machine learning videos that will be in the series, definitely like this video and subscribe to my channel, and also hit that notification bell so you're notified whenever I'm posting a new video, which I think will be Mondays and Thursdays at 12 p.m. Eastern if I'm on time. That's it for this video, and I'll see you on the next one. Later.
I wanna take you home to mama. I wanna buy you diamond rings. Make sure that you're happy. Show you everything.